please have your notes page called Introduction to Capacitors in front of you. And if you haven't had a chance yet, just go ahead and read the top that defines capacitance again and introduces the idea that we're going to be using Gauss's law to also develop the idea of capacitance, specifically for the oppositely charged parallel plates. So I know Gauss's law can look a little bit scary, and we've only used it really once before. All right, so now we're going to use it a second time, and it's not going to be too bad. You'll see, it's not bad at all. So on your page, you already have a sort of a almost complete picture of the oppositely charged parallel plates in their field, and what's going to happen with this. I'm just going to start from the beginning here, break it on down. So the idea is, let's start with drawing, well, I'm going to draw on the screen here, one of the plates, and we're looking at it sort of in 3 dimensions, not from the side like we usually do, and we'll say that this plate has an area A, and then we charge it up positively by bringing a whole lot of electrons off it, so it's got an overall charge positive Q, and that charge is just spread all throughout. And then to do Gauss's law, what we do is we enclose it in a Gaussian surface, an imaginary surface through which electric field lines are going to pass. And since this plate, this sheet, has sort of rectangular symmetry to it, the easiest way to do this is by building basically like a rectangular box around it. The first time we done Gauss's law, it was for an individual point charge. And so we built an imaginary sphere around it because it had sort of a spherical symmetry. So we try to match the shape of this Gaussian imaginary surface to the shape of the conductor, or the charged object itself. And so we want to imagine this as being like sort of like a packing box, and we snugly fit this sheet into it, just barely fits inside of it. And so you can see that the top side of this box would have an area A as well, and the bottom side would have area A as well. Don't worry very much about the sides of it, because when we draw the electric field, which of course, since being positive has field lines that point outwards, we're going to assume that this is so thin here that there's no field coming out the sides, the front, the right, the back, or the left, only field lines coming out the top of the box and field lines coming out the bottom of the box. I hope you can visualize that, right? These are electric field lines that are sort of piercing the bottom of the box, and here's electric field lines piercing the top. We talked about with the beach ball, these being like sharp pointy sticks creating holes, right? But here's like something creating holes in the box. Hopefully this makes sense. Okay, so now what we're going to do is we're going to use Gauss's law, which says we add up all the bits of area through which electric field lines are piercing, and that's going to be equal to the charge enclosed divided by this term, epsilon naught, which is the permittivity of free space. And while this looks all scary, it really isn't. This just says we're going to integrate the bits of area through which electric field lines are poking. And again, assuming that there's no field lines coming out the sides or the front or the back of this, field lines are only coming out the top and coming out the bottom, well, this is not difficult at all. We're just basically adding up the area of the top of the box and the area of the bottom of the box. And so field lines pierce the top of the box, that's one area, A. Field lines are piercing the bottom of the box, that's another area, A. And so when we integrate that and we add it together, that's just E times 2A. That's it. Really easy. We're done with the integral. Great. What's the charge enclosed? Well, this box snugly fits all around the entire sheet, the entire plate, so it's just Q. So it's Q over epsilon naught. So easy, so simple, not bad at all, right? It can get more complicated, but not for what we're doing. So we solve this for E, just move 2A to the bottom, and so I write it as E equals Q over 2 epsilon naught A. I just like to cluster the constants together. Okay, that's it. That's the field produced by the positive plate. E equals Q over 2 epsilon naught A. Now, of course, for oppositely charged parallel plates, we have not just the positive plate, we have the bottom plate as well, the negative plate, so I'll draw that over here. So it's the same idea. I'll enclose it in this snugly fitting box. It also has an area A, and it's just covered in negative charge. We draw its electric field. Since the charge is negative, the field lines point inwards, and again, we make this assumption that the sheet is skinny enough, it's thin enough that no field lines come out the sides or the back or the front, only inwards here, inwards here. And we're going to apply Gauss's law again. We add up all the bits of area of the box through which electric field lines pierce. And once again, hopefully you can see, we only have field lines piercing through the top part, which has an area A, and field lines piercing through the bottom part, which also has an area A. And so it's going to be E times 2A equals Q over epsilon naught. In other words, we're going to get the exact same results. You can prove it to yourself if you'd like to, but hopefully you see there's really no difference. The direction is different, but because here field lines are flowing in, here field lines are flowing out, but the magnitude of the field will be exactly the same. So hopefully you see that, right? So the positive plate creates a field of this magnitude, the bottom plate creates a field of this magnitude as well, and now all we're going to do is put it all together. So let's look at a few different regions. Let's first look in the region above this whole system. So the positive plate in this region creates a field, like we just said, Q over 2 epsilon naught A. But now I want you to think about the bottom plate, the negative plate, this field, these field lines, we can imagine extending them all the way up to the region above the top plate. Can you visualize that? Can you see that? Can you imagine that, right? So this bottom plate, independent of the top plate, creates a field that can extend all the way up there, and we already know its magnitude is also Q over 2 epsilon naught A, but the positive plate creates a field that points up, and the negative plate creates a field that points down. So if you think about them as vectors, because of course they are, one of them being positive and negative, well, what should we do with these magnitudes? They're pointing in opposite directions. Yeah, we're going to have to subtract. Consider like an arbitrary direction as like up being positive. You want to think of it like that, right? So here's positive direction, this amount. Here's negative direction, this amount. And what's going to happen? Well, those fields are going to cancel. And you might have noticed every single time we draw the field for oppositely charged parallel plates, we've never drawn a field above it. And this is why. Because the fields do cancel out to zero. Let's look in this region down here below the negative plates. Well, we know the negative plate creates a field of Q over 2 epsilon naught A, but so does the positive plates. And again, I want you to imagine extending these field lines all the way down to this region below. Well, the negative plate creates a field pointing up, positive plate creates a field pointing down. They're in opposite directions, and once again, I hope you can see those fields are going to cancel out to zero. And once again, you think, oh yeah, we've never drawn any field below the negative plate when we draw the oppositely charged parallel plates, and this is why, because the fields cancel. So there's no field above, there's no field below. What about in between? Well, how do we always draw this? We draw field lines pointing from positive to negative, because in this region you can just imagine extending and connecting all of those field lines. This is really how we usually draw it, not in 3 dimensions, like all fancy like this, but that's it. Field lines pointing from positive to negative, all I did, like I said, was connected the lines in this region between. Because what happens is the positive plate creates its field of Q over 2 epsilon naught A, and the bottom plate, the negative plate, creates also a field of Q over 2 epsilon naught A. And how are they pointing? Well, the positive plate creates a field pointing down. The negative plate creates a field pointing down. Now we're adding them. Those fields are pointing in the same direction, right? They're combining. And so, if we add these two field magnitudes together, well, what do we get? Hopefully you've already done it, you figured it out. It's just Q over epsilon naught A, right? Half plus half equals whole. Just in case the algebra was bothering you. So there we got it. We got the field strength between oppositely charged parallel plates as being equal to Q over epsilon naught A. But wait a second. We've done this before, back in our previous topic, right? We had an expression for the electric field, this uniform electric field between oppositely charged parallel plates, as just being delta V over delta D. Well, that doesn't go away. As like we just showed, when we connect these plates to the source of voltage, the battery, we get this potential difference delta V, and delta D is just the distance of separation between them. So these are both equivalent to each other. So what do? Set them equal to each other, right? That's it. Now, it was a little sneaky. Do you notice I lost something? Yeah, I lost this delta, and that was on purpose. Why did I lose this delta? Well, in the previous topic, we had the oppositely charged parallel plates, and we'd often put some sort of point charge in between them, let it go, and it would go from one plate to the other, traveling a displacement of delta D from one plate to the other. But in our new topic, as I was mentioning before, that's not happening. The electrons are held against the well on this plate. They've left the top plate, leaving behind positive charge, and there's air in between. And the electrons cannot jump the gap from the negative plate to the positive plate, so nothing is actually going to be moving from one plate to the other in our new topic, because there's air in between, there's insulating material in between. And so I dropped the delta from this, just saying that D then is just the distance between the plates. A delta implies something moves from one plate to the other, so I dropped that out, saying, nothing's actually moving, so D is just the distance. And now, I'm just going to rearrange a little bit, and you're going to do that as well. I'm going to swap the delta V on the right-hand side with epsilon naught A on the left-hand side. Go ahead and do that. And we're left here with Q over delta V equals epsilon naught A over D. Why do we do that? Well, hopefully you see Q over delta V. Oh, yeah, that is capacitance. And so if this is capacitance, this one is as well, right? C equals Q over delta V, so now we could also say C equals epsilon naught A over D. The first equation described what happened. We connected the uncharged parallel plates to a source of voltage, and charge moved around. creating a charge separation, some amount of charge on each of the plates, creating a potential difference or a voltage between them. That's the physical what happened, right? This only deals with the actual parameters of the plates themselves. A being the area of one of those plates, and D being the distance between the plates. This is linked directly to just how big the plates are. Their capacitance, I should say, to store energy. The larger the plate, the more charge can be pulled off it. The closer they are together, the stronger field they could create, and that all correlates to a larger amount of capacitance. Now, to be very clear, this equation is only for the parallel plates. I say that for a couple of reasons. One, this here is the definition of capacitance. It can be used in any situation at all, regardless of what's happening. This one here is only specifically if we have oppositely charged parallel plates, or really just plates in general. They don't even have to be charged. And I say that because in other classes, future classes of physics, you'll learn other geometries of shapes of objects that will also have a capacitance, and this equation will not hold. At our level, we're only going to be dealing with what we call parallel plate capacitors, so we can always use this, but just to be clear, there are other situations that could occur.